Welcome to the Explainer, everyone. I am absolutely thrilled you're here today. We're actually tossing out the usual agenda completely because I want to get straight to the heart of one of the absolute biggest pain points in programming, especially in embedded C. We are talking about how we handle massive, overwhelming amounts of data without, completely losing our minds. It's all about arrays. We're going from simple variables to continuous memory blocks, and we're going to explain the whole shebang visually, so strap in.
Okay, let's dive into this. Section 1, the 100-variable problem, and how we handle massive data.
Imagine you're building a system and suddenly you need to collect a frantic, nonstop stream of data. Without the right tools, it's an absolute nightmare. So ask yourself, how do you store 100 different sensor readings? Just imagine the sheer chaos of typing out sensor reading 1, sensor reading 2, literally all the way to 100. It's a completely impossible burden, right? It makes your code super prone to errors and, honestly, just a total headache to debug. But instead of that impossible headache-inducing burden of 100 separate variables, we have a clean, absolutely heroic solution. One single array. Sensor 100. I mean, that is the beauty of it right there. With one simple line of code, you instantly create this perfectly organized, highly efficient container for all 100 readings. It is a total game changer for code readability and efficiency. Moving right along to Section 2, memory layout and zero indexing. So now that we've solved the problem conceptually, let's look at the anatomical mechanics of it all. Every array goes through 3 fundamental phases in its life. Step 1 is declaration. This is where you basically tell the compiler, hey, I need a block of space. Step 2 is initialization, where you actually fill that space with your real-world data. And step 3 is indexing. Think of this like a perfectly organized neighborhood of continuous memory blocks. When you declare an array, you are literally reserving a continuous row of houses on a street, all lined up perfectly next to each other, just waiting for residents to move in.
Now, if you've dabbled in programming at all, you've undoubtedly heard the rule that arrays always begin at index 0. But let's pause for a second. Let's treat this not just as some arbitrary, boring fact, but as a genuine revelation about how computers actually think. I mean, why 0? Why wouldn't we just start at 1, exactly like how we count objects in the real world?
Well, what's really interesting about this is that the answer is entirely driven by memory addressing. Inside the hardware of your computer or microcontroller, the index isn't just a simple count of how many items you have. It's actually a mathematical offset. It tells the processor exactly how far away a specific memory block is from the very beginning of the array. So that first element, it is exactly 0 steps away from the start. It's right at the starting line. It's this brilliant, highly efficient quirk of hardware memory addressing that saves precious computing cycles.
Let's move to and see how this builds in Section 3, 2D arrays and complex structures. So how do we scale up from a single, flat street of memory houses to much more complex structures? Imagine a 3x3 table filled with binary zeros and ones. It's a perfect metaphor for a 2D array. Instead of a single row, you now have a grid, kind of like a chessboard. And this flawless structure maps directly to real-world components in embedded systems. If you're lighting up an LED matrix to, say, display a smiley face, or if you're storing the pixels of a digital image, you are using exactly this, a 2D array mapping out coordinates in continuous blocks of memory. And then, of course, we have character arrays. This brilliantly demystifies something that honestly trips up a lot of people: strings. You see, in languages like C, a string isn't some magical, ultra-complex data type. It is defined simply as a character array. It's just sequential memory blocks, but instead of being filled with numbers or sensor readings, they are filled with letters, numbers, and symbols, characters, strung together to create human-readable text. So how do we actually use these character arrays in practice? Well, they connect directly to tangible outputs. When your smart thermostat pushes 72 degrees to an LCD screen, or when your microcontroller shoots diagnostic messages to your computer over a UART serial line, it is literally pushing arrays of characters out into the real world. Character arrays are the communication lifeline for sure. They're the actual voice of your embedded system. And this brilliantly illustrates our next point in Section 4, embedded examples and real-world apps. Okay. We've covered the core theory and hardware indexing. Now let's see how embedded C relies on this every single millisecond. Let's fire these off because this is exactly why everything we just learned matters so much. Need to smooth out noisy, jumpy data? You use a sensor buffer array. Grabbing analog signals like audio from the real world? You store those ADC samples directly in an array. Processing complex audio frequencies? That requires feeding data right into a fast Fourier transform or FFT input array.
Or hey, how about controlling the exact brightness curve of an LED or the speed of a motor? You use a PWM lookup table, which is really nothing more than an array holding duty cycle values. I mean it. Arrays literally run the hardware you use every single day. Let's bring it home with Section 5, the pointer connection, the underlying engine.
Let's just lower the pacing for a second here, because as we reach the peak of realizing just how powerful arrays really are, there is this deep mystery beneath everything we've discussed so far. So the crucial point is, the underlying engine of every single array is a pointer. All those continuous blocks, the mathematical zero indexing, the hardware memory addressing, it all functions because an array name, at its very core, is actually just a pointer. It points directly to the very first memory address of that block. Pointers act as the true connective tissue navigating all these continuous blocks of memory. Which brings us to a really provocative question that I want to leave you with to synthesize this whole journey. If arrays rely on continuous blocks, and we now know that pointers are the true engine behind them, how exactly do pointers navigate that memory? What is the literal math happening under the hood to jump flawlessly from one memory address to the next? It's a fascinating cliffhanger that bridges the gap between basic arrays and advanced memory manipulation. Thank you so much for joining me for this explainer, and I really hope this leaves you eager to uncover exactly how pointers work next time.